Welcome to Chapter 16. This lecture is going to be about population ecology. So let's get started. So right across the top here, it gives us this broad question of what is ecology? And as we know from the title of this chapter, we're going to be talking about population ecology. But what is ecology? Well, the next slide is going to give us a nice description and definition, but I'm also going to give you one. So write down ecology is the study of interactions between organisms and their environment. That's the big important thing. So what ecology is a relationship. So it's that relationship between organisms and the habitat, the environment that they live in, right? So what ecologists are tasked with doing is determining certain factors about the relationships of organisms within their environment, as well as population numbers. What number is required to allow for an environment to be considered healthy? How can we maintain that environment with those organisms within that environment? What is needed in that environment? If we take something out, what will happen? So that is the big heavy hitter of ecology, looking at those relationships and how modifying those relationships can affect the organisms in the environment as well as the environment itself. As promised, this slide is going to give you that definition that I gave you on the previous slide of what ecology is. But one of the ways that we can study ecology is on different levels. And those levels start from a more specific focus and go substantially more broad in how we view ecology or looking at an environment based on the perspective of ecology. So that starting scope is going to be an individual, so individual organisms. Then we kind of zoom out a bit into populations. And populations will be groups of individual organisms that interbreed with each other. And you can write down the word species since we just learned that in the last chapter. And then from there, we zoom out even further and we come to the term community. And community or communities are going to be populations of different species, so organisms that cannot interbreed but do interact with each other within a locale. And then when we zoom out even further, we look at an ecosystem. An ecosystem is going to be all living and non-living elements within a particular area or locale. So we're going to come across two terms eventually. I don't believe in this chapter, but those are the terms biotic, B-I-O-T-I-C, and abiotic, so you just put an A in front of biotic, and that's going to refer to living and non-living, respectively, parts of an environment. In talking about ecology, we do want to focus, much like we did like evolution, instead of on individuals, we want to focus on a population perspective. So we are going to start shifting more into population ecology, much like the chapter title indicated. And what that means is we're looking at how populations of organisms of a species interact with their environment. Instead of just an individual interacting with their environment, we're looking at a population interacting with their environment. This is going to be important in looking at how a species regularly is exchanging their genes within a particular locale, and how that is going to be affecting that locale, specifically that environment. In looking at ecology, remember that we want to start to question how many of a species do we need to have within a population to have a healthy environment, which is going to lead us to looking at how populations grow as well as what is going to affect that growth. So let's start looking at population growth and the fact that populations can grow very quickly, especially for a time, but more often than not, populations cannot maintain this heavy growth forever. In fact, we're going to give you this term, a stable population, and what that means is that a stable population is going to be when an individual replaces itself. So if we have a mating pair of, let's say, rabbits, and the mommy and daddy rabbit are having two baby bunnies. They have a boy bunny and a girl bunny, and they just replace themselves. And that's as many baby bunnies as they have for their entire life. Then in that population, as long as their children also just replace them and their baby bunnies also replace them and so on and so forth, that population will just be incredibly stable. That population will technically not grow. It will be just a stable population. But we know that in most populations, especially in something like rabbits, that the bunnies will not just replace themselves, they will have more offspring than just the two of them, right? So, in that instance, we see that population growing. So, if we have populations that do more than have stability, so we have individuals that are doing more than replacing themselves, having more than two offspring per pair. So they're having maybe 3 to 10 offspring per pair. Why is the earth not swamped with an overwhelming amount of, let's say, rabbits? We're going to find out why. So, how a population grows and also shrinks um, if individuals do more than just replace themselves. So, having more than two offspring per mating pair, we need to talk about a few things that go into determining the population growth or shrinking. So, this first term in the red box is going to be growth rate. That is the change in the number of individuals in a population during some unit of time. Growth rate is going to be abbreviated as a lowercase r for the purpose of our equations that we're going to be coming up on here soon. The next term we need to look at is population growth, and this is going to be something that we calculate. And in order to get population growth, we're going to need to have two pieces of information. The first is going to be that first part that we talked about, that was growth rate, so lowercase r. We're also going to need capital N, which is going to be the number of individuals in the population technically at that time. But for now, just realize that N is the number of individuals in the population. In order to calculate population growth, you're just going to take R and multiply it by N, very simply. But we are going to make it a little bit harder, I believe, on the next slide. I say harder, but I promise it's not as hard as it actually looks. And I promise we'll walk through every little piece, and I might even try to do a little fin dangling with my mouse. So bear with me as I figure things out here on my side. So we are going to be calculating population growth rate here. While at the same time I'm going to be walking through an example. And normally in an example, I would give you an animal per se. So I wouldn't just say 500 individuals of some indeterminate species. I'd give you some animal like 500 rabbits or 500 lunar moths or something like that. I'd give you some animal. But in this case, we're just going to say 500 individuals. We could say, let's say elks. So 500 individual elks in a population. This gives us N of 500. So from there, we need to figure out a few things. We need to figure out the birth rate. We need to figure out the death rate, and that will then give us the ability to get the growth rate. So in order to get the birth rate, in this word problem, we need to be given this information. So we were given N equals 500, and we will also have to be given the number of offspring born. Pardon my terrible circle. So we have 125 offspring being born. In order to get the birth rate, we are going to take that 125 and put it over 500, and the 500 is going to be N. So it's going to be the number born over N. Okay, that is how we get our birth rate, which gives us 0.25. Remember, don't leave your decimal points naked. Always put that 0 there. So we get 0.25 births, and this is kind of a funny phrasing, but per person. We'll say per elk. We'll say elk. We're looking at elk at the moment. So from there, we have our birth rate. Easy peasy. Check that off. We're done. From there, we want to get our death rate. We are going to be given that information. We have 25 deaths going on. So 25 is going to be the top part of our division for our death rate, and then the 500 is going to be the bottom part. Again, that is coming from our N equals 500, and that's going to give us 0.05 deaths. From there, we're taking, and let me change my color here, we're taking these two numbers, so our 0.25, our 0.05, and we're going to plug that in to our growth rate equation, if you will. So we're taking our death rate, we're going to minus it from our, we're taking our birth rate, I apologize, our birth rate, minusing it from our death rate, and that's going to give us 0.20. So that gives us R. So R is going to be 0.20. What we do with that information, remember that it's going to be R multiplied by N. Ooh, this is hard to do with a mouse, but I'm impressed with myself. So we take 0.20, multiply it by 500, and that's going to give us 100 individuals going to be added to the population in 1 year. Now, keep in mind that when we're talking about calculating population growth rate, we're estimating what we think the growth of the population might be in some amount of time. This is an estimate at best. So this is our best guess in 1 year how many elk, based on the information that we had from here, how many elk will be added to the population in 1 year. Now you'll see why I said elk, and it sets us up for this slide where we talk about unchecked population growth. And when we talk about unchecked population growth, what we're talking about is something called exponential growth. And what exponential growth is the bigger the population, the faster it will grow. Or, as the slide says, a population size increasing at a rate proportional to its current size. So a larger population is going to increase much quicker. And what we see if we graph that out is this J curve, and you can see that that exponential growth curve is that J curve. If we took the numbers that we had on that last slide of calculating population growth rate, and we plugged it in for 10 years from now, 50 years from now, even 100, what we would see is exponential growth of elk potentially. It would be really wild, really crazy, and elk would become the dominant species on Earth and overrun everything, and they'd be our elk overlords essentially, which, if you can imagine, unchecked population growth is a bad thing. In saying that, though, we need to understand that that is not a normal way that populations grow. It will not happen for a long period of time, and there is a reason for that, which is the fact that there is a lack of resources. So resources on Earth limit the growth of populations. And what we call this is logistic growth when we graph it out. The ceiling that curve, that J curve, ends up hitting and plateauing at is called carrying capacity. Carrying capacity we will talk about a little bit more in just a few slides, but realize that on this graph it is that orange line that J curve is smacking on into and turning into an S curve, which we call the logistic growth. So this is how we limit our unchecked population growth, how that doesn't go unchecked. So let's talk about what those limits include. As you can imagine, those limits are going to be what the environment has to offer, as well as a handful of other things. So primarily we're talking about food and food competition, as well as potentially water. Water might also be in that area of competition, as well as an increase in competition over places to live. Some animals are very particular about where they will live, as well as where they will breed. Many birds and other species will be very particular about where they build nests and where they will breed, which can be very limiting if they are particularly picky. So in populations that are a little bit too large, or in habitats that are getting a little bit too small, that can become a very big factor in population limits. Another factor is if a population is getting too large, we can see an increase in disease and parasites because of the density of the population. We see more hosts for those parasites and diseases to hop from one host to the next. So if we have a high density population, we see substantially more diseases going around, more parasites as well. And then, of course, we also have a higher risk of predation in higher populations. So more risk if there is more of the population to be consumed, essentially. But there is also a limit if there is too high of a predator population as well, and we'll talk about what that looks like here in a second. When we study population growth, there are a few terms that we want to go over. One, I already said on the last slide, I just used it, and that is density. So population density is going to be the number of individuals in a given area. So if that density is particularly high, that means that there is quite a few individuals within that locale, which could be a good or a bad thing. It depends on what we're looking at, if we want a higher density or not. That leads us into what is called a density dependent factor. These are conditions that limit population growth due to the population size in a given area. So I want you to really focus on the fact that it's density dependent, because we're going to come across a term on the next slide that has nothing to do with density, but density is in the title. So keep them separate. So density dependent factors have everything to do with the size of the population, and they limit the population growth because the density of the population is too high. And normally what will cause that density dependent factor or factors to come into play is the carrying capacity, which when we get to the equation that will involve it, we represent it as the letter K, but we'll get to that when we get to that. So carrying capacity is going to be, as I said before, that little cap, that ceiling on growth for a population in a particular environment. And usually it has to do with limiting resources, right? So again, kind of keep in mind that density dependent factors are going to be conditions that limit that population based on the population size. Density independent factors, however, are going to be completely independent of the density. So they have nothing to do with the population size and everything to do with essentially bad luck events. These are usually weather-based or geology-based events. They're kind of by chance. And again, I really like this term bad luck events, but they are chance events like maybe a fire or a flood, maybe an earthquake, that will cause habitat destruction and death and limit the population size, but it's completely based on the weather and not on the population size. Very important. Now, I know this slide looks really overwhelming, but the big thing that I want you to pay attention to, and really the only thing that I want you to take from this slide at the moment, is going to be this third bullet point, and that is this equation right here that I'm circling in blue. So it is going to combine the little equation R times N to get population growth, which we've already looked at, and it takes into account carrying capacity when we look at population growth. So it gives us more of a realistic approach and look at population growth, because it takes into account that ceiling that we can hit with a population. So that is the most important thing I want you to get from this slide. I'm not even going to talk about the other things on here. Not that they're not important, just that is the one thing I want you to write down, and we will get to an example here in a little bit. And by a little bit, I mean the next slide. So pause on this slide, and what I would really like for you to do at home is to practice and write out what you see, what information you're given, and then apply that information to the equations that we've gone over. So remember, we're trying to get R first. You're going to need the birth rate, and then the death rate, and then that is going to give you R. And then once you have R, you can get the population growth, R multiplied by N. And then once you have that, you're going to be able to kind of plug and chug because you are being given K. So kind of keep that in mind. You have to go in order. If you go out of order, it's going to throw you all off. So go ahead and pause on this slide, and then the answers will be on the next slide. Now, I'm hoping you showed your work when you went through that last problem. And if you didn't, hopefully you see what you did wrong. If you have a question, would like to ask me about what you potentially did wrong, or maybe we can go over another example, I would love to do that with you. Otherwise, there will be a problem exactly like this on the exam. It will be short answer, not multiple choice. So you will need to be able to show all of your work. You'll need to show me what equation you used. You'll need to show me what numbers you plugged into the equation, and then you will need to get the right answer to get all of the points. So there are 3 things you have to show me for every single part in order to get all of the points for the short answer problem on the exam. The growth of populations doesn't always appear as smooth as S-shaped logistic growth curves. For some populations, particularly humans, our carrying capacity has never really been set in stone. We keep pushing it back and kind of defying the odds and defying the science, if you will, of what our carrying capacity as well as how large our population can grow to and where our populations can expand to. Which is really quite interesting as far as a species goes. It's not always the best thing for other species that we've done this. And the reason I say that is one of the main reasons that humans have been able to fluctuate our carrying capacity is through our advances in agriculture, which, fabulous for us, not always so fabulous for other species. So our ability to push our carrying capacity may have tanked the carrying capacity of environments for other species, which, kind of a catch-22 when it comes to how that could affect us in the future. Some populations are not always so textbook in their growth patterns. Some can be incredibly unpredictable. One of the examples that we have is these locust swarms from 2004. They increased rapidly across the deserts of the northwest of Africa, and due to unusually good rain and mild temperatures, their populations just boomed, just absolutely exploded. It was like the most fabulous weather caused a lot of growth of vegetation, and so the locusts were able to reproduce and have this massive exponential growth in this particular season. But as the rainy season ended and as the green areas began to shrink, the locusts became heavily concentrated in these smaller, dwindling green areas, which then became eaten up by the locust. And once consumed and gone, the locust then had to search for other areas to find food. So, driven by hunger, and populations unlike anything they'd seen in many years prior, the locust, which were usually individual or singular species began acting like a pack or a mob. And this unusual behavior then caused them to swarm farms and other places that they would not have normally swarmed, and caused about $100 million in damage. Which, all that to say, this was just a very odd cycle of, like, used to be very small, then just a massive population boom, and then we're back to about 20 years since then of a smaller population of locusts. But during that odd season of rain, it caused the locust population to just explode. So things that can affect populations, definitely the weather, definitely things that we have no control over can affect populations, and thus the populations can then affect us or the environment, which is kind of neat and also sort of terrifying. Now, your book calls this an unusual pattern, but I think it's really beautiful and quite interesting, and it's one of my favorite things to say. And if you're listening to this at home or watching this at home, I highly encourage, and if you end up getting to enjoy this lecture in person, I also encourage this in person to say this term, but population oscillations. It's just a fun set of words to say together. So it kind of just tickles the tongue, just rolls off quite nicely. So if you feel like saying it, just go ahead, say it with me. Population oscillations. So what this is, now that we've said it a few times, is this cycling effect, if you will, of relationships, usually between species. And the one that we're going to look at is a predator-prey relationship that cycles between each other. So what we have is a relationship between a lynx and a hare. The lynx, if you're unfamiliar, is going to be that really cute tailless cat, and the hare is the rabbit in its mouth. So the cat, the predator, is going to essentially the population of the cat, the lynx, is going to follow the populations of the hare. Now, what happens with this is as the predator population consumes the prey population will decrease. From there, there is less food. So the predator population will then drop. Once the predator population drops, the prey population will increase because there's not as much predators to consume them, so they are able to reproduce more. Once the prey population starts to increase, well, now there's more food for predators, so the predators will then increase in population, and thus that cycle just kind of oscillates around each other. So what we see is the hare and lynx population rise and crash in about a 10-year cycle, which is kind of neat. So that is a population oscillation, which I think are really neat, but again, your book thinks it's unusual. I just think it's cool. When we talk about K, which is carrying capacity, as well as N, it's important to note that both of these values are very rarely ever known. It's difficult to know for sure what the population number of any given population generally is at any given point in time, beyond a shadow of a doubt, unless you have a species, maybe like grizzly bears, say in Yellowstone. Those can be generally easier to keep track of, as those animals are a smaller population, they're a larger mammal. Their movements are a little bit easier to track. as well as it's a smaller area. I say smaller, but Yellowstone's massive, but it's a generally smaller area to be able to track a larger animal, relatively speaking, as opposed to say like all of the squirrels in Yellowstone. That would be like darn near impossible to figure out. When we look at the value of K, it would also be really difficult to be able to figure out what K is. So normally K, carrying capacity, is going to be something that we guess. And it's also hard to say what carrying capacity would be year to year because it could be unstable one year, it could be completely different another. We just don't know. So, in looking at these two values, just kind of keep in mind when it comes to the equations that you'll be given, the values of these numbers. It is just me giving you that number. And usually, when those numbers are presented, it is just a guess. All right, moving on to something a little bit more interesting, I think. Maybe you'll like this. And that is a species life history or an organism's life history. And when we talk about a life history, what this is talking about is a species' vital statistics. And what those statistics include are the age at first reproduction. So you can kind of think of puberty, although for most species they don't necessarily go through something like human puberty, but essentially the age at the first opportunity that that animal is able to produce offspring, and typically they do. The second is probabilities of survival and reproduction at each age. The next is litter size and frequency of litters. So, how many times can they reproduce in some set amount of time? And then longevity. So, when we talk about longevity, we're talking about how long that species or organism is going to be expected to live. So, one of the things that we want to also talk about here when we talk about reproduction, because we're going to start talking about reproduction quite a bit here in the next little bit, is reproductive investment and what reproductive investment is when it comes to the life history of an organism is all of the material and energetic contributions an individual will give to make offspring. So, for males and females, reproductive investment is vastly different depending on the species. Typically, females will give a lot of reproductive investment for gestation and in the form of energy. So their bodies are usually what houses the offspring as the offspring is formed, as a smaller organism, so like a fetus, and then from that point, they go through that reproductive investment of birthing, and then nurturing, potentially producing milk, whatever that may be. There's quite a bit of reproductive investment in many mammal females. Now, when we talk about reproductive investment in the different ways that some life histories have in the form of reproduction, which we'll see on the next slide, it does seem like some males give a lot more than the females, and you'll see what I mean here in just a second. So, life histories are shaped by natural selection, and remember, natural selection can come in the form of sexual selection as well as from predation. So, it just depends on what we're looking at. natural selection is going to weed out various things that make it to where that species is either better or worse at surviving. It just depends on what we're looking at, and usually there are trade-offs, and we'll talk about those trade-offs here in a minute. So there are three kind of variations of reproduction within our life histories. And the first is the Big Bang reproduction, which is very silly to call it that, but I mean, it's enjoyable for what it is. And this is where that reproductive investment for males is really quite the catch. So the example that we have is the Australian mouse. It is a marsupial. He's a real cutie pie right there. And what happens is they reach sexual maturity at 1 year. The males will mate intensely over a 3-week period, and over that 3-week period, they will have 12 hours of copulation at a time. And then, once that 3-week period is up, they will die. So their reproductive investment is to mate with every female they come across, mate as long and as intensely as possible, and then to die. So they have one very intense mating season, and then it's gone. That reproductive investment is very interesting. They give it all, so to speak. So from there, the females will then give birth to their litter, and potentially die after weaning, meaning they finish producing milk. The babies or pups, maybe. Not sure what mouselings, what baby mice are called. But pinkies, I don't know. Either way, so the baby mice will stop taking milk, and potentially the mother will die, but in some cases, sometimes the mother will go through another mating season and then pass then. But that is the Big Bang reproduction. There's a lot of risk, a lot of reward for that style of reproduction, especially for the males. And we can see why. The next is fast intensive reproductive investment, and the example we have here is the common house mouse. They reach sexual maturity at just 1 month, that's right, 30 days of age, and they produce litters of 6 to 10 offspring every month after that first month. But their life expectancy is roughly a year or two, if that. So remember that when we look at these first two species, they are also prey species, which means that their life expectancy is very short. Not only are they prey animals, they're also very small, and typically small animals are going to have a lower longevity, like a smaller longevity, a shorter longevity, if you will. Our last reproductive life history variation is slow, gradual reproductive investment. The example we have is the little brown bat. They're quite cute as well. They reach sexual maturity at 1 year, but they can live up to 33 years, and they produce one offspring per year, potentially, if they reproduce. So their gradual, slow reproductive input is very rewarding, but they also have a longer gestation period than, say, our mice would, and their reproductive investment is a little bit different. So kind of fun, kind of interesting. If we were to ask the what I consider to be odd question of which life history strategy is best, we have to take into account two more questions in echoing that first question. And that is, what is the cost of reproductive investment during any reproductive episode? So if you are that Australian mouse, that reproductive investment, that cost is very high. You give your life for your reproduction, right? So that cost is a very high price to pay for that big bang style of reproduction. The second question we have to ask is, what is an individual's likelihood of surviving to have future reproductive episodes? So when we talk about those prey species, what we're saying is, how likely are you to make it to your next season to reproduce? Obviously, with the Big Bang reproduction, we know that the reproductive investment is going to cost that species their life. But the likelihood that they actually produce offspring is incredibly high. So they do move their alleles, their genes, into the next generation. That's almost guaranteed. The other styles of reproduction may not. It just depends. But because they live longer or they reproduce more, like once a month, then the likelihood of surviving or having reproductive episodes in the future increase greatly. So natural selection is going to favor lifetime reproductive success. So we see substantially more species that display that latter, that third slow, gradual investment, or that middle investment, as opposed to that big bang. We do still see species that do that, but not as much. I mentioned before that in talking about these life histories, we have to talk about trade-offs. And when we talk about trade-offs, we have to remember a term that came up in a previous chapter, and that is fitness. And remember that fitness is an organism's reproductive output relative to the others in the population. So if we consider trade-offs between growth, reproduction, and longevity, we need to keep in mind that evolution is going to function in such a way that it may favor one of those features, but then it will adversely affect one of the other features. So, in keeping that in mind, if we were to design, and this is kind of silly of your book, if we were to design a species and give it all of the best things of all the life histories, then ideally this organism would produce a ton of offspring all the time and be able to have offspring the second it gave birth and all the time, every year, always. It would grow tremendously large so that it couldn't be eaten by another animal. It could not be prey to a predator, and it would live forever. And, the sky would rain gumdrops, and the water would be soda pop, and, there would never be anyone hungry, and everyone would feel loved, and everything would just be rainbows and butterflies. But that's not how things work, because that's not the world we live in, and there's reasons why. It's because of these trade-offs. So let's talk about what these trade-offs look like with those various reproductive styles that we saw before. With the Big Bang uh, reproducers, another example is salmon. And what salmon do is they put all of their energy into swimming into their original freshwater streams. So they swim upstream to where they were hatched as little fishlings. And from there, the females release their eggs, and then the males then release their sperm, and then they just up and die shortly afterwards. So what happens with this is we have this trade-off of reproductive investment being very high, but then there's death. So that is the trade. The next example we have is reproduction and growth. So we have beech trees and how in the years that they produce seeds, so when they reproduce, they don't grow very big. They don't grow very much at all. They grow very slowly. Then in the years that they do not produce seeds, so they are putting their energy into producing seeds versus growing. And what we see is that as a trade-off that the trees will forego growing to produce offspring. Our next example of a trade-off is this type of lizard will produce a smaller egg, and she can produce more of these smaller eggs, but they have less of a chance of surviving than if she produces larger eggs, but she can only produce a limited amount of the larger eggs, but they have a higher chance of surviving. So that is her trade-off with the number and size of her offspring. Moving on to less of a trade-off and more of why it is we have this term longevity. What is aging? Which is to say, why do some species live to a certain age versus other species? What is aging? So from the standpoint of humans, when we think of aging, there's both a physical and mental idea of aging. We can think of a physical aging as maybe sagging skin, graying hair, maybe cataracts, teeth kind of getting worn down, hunching shoulders, things of that nature. When we think of mental aging, we can maybe think of senility, dementia, things like that. But the one thing that we can for sure say is that no two people age the same. Yet we all age. We know that humans age. And if, potentially someone doesn't seem like they're aging, maybe that's, Botox or something like that, or really good skincare, who knows? But we know that aging is happening. So we kind of have to look at aging on a population scale. And that's what we're going to look at next. So from a population perspective, aging can be classified as, and I think this is kind of a cute way of saying it, an increased risk of dying. So that's what aging is. So as you get older, you have an increased risk of dying. So you have a higher chance of dying at the age of between the ages of 45 and 46 than you do at 35 and 36, and so on and so forth. You can kind of keep saying that as you increase in age until you get to a much older age and say, well, yeah, that's kind of a reasonable age for a human to reach and then to pass. But why is it typically an average age that we get to thereabouts. So we can look at the ages of different species and kind of assess various features about them. So for humans, what's sort of interesting is the average age of death is around 80. So it was about 78, but we'll just round, even though you know I don't like rounding if you know me well enough. And if you want a little fun fact, Jean-Louise Calment, or maybe Jean-Louise Calment, depending on where she was. Sorry, I didn't do as much research as I should have. Was 122, and she is he was the oldest person documented in recorded history, which 122 is nothing to sneeze at. So that is a pretty ripe old age, I'd have to say. Nothing like the bristlecone pine tree, though, which was recorded to be 7,000 years old. Lobsters and quahogs, which are a type of clam, can reach 100 or 200 years old, respectively. And striped bass and tortoises can reach 120 or 150, respectively. Meanwhile, rodents and birds typically only live a couple years, depending on the bird, of course, and bats can live around 30 years old. So everything's kind of depending on what species we're looking at, depends on what age we're seeing. But why do all of these different species have such variety of those ages that they typically will live to and then die? So why do they get to that age and then that risk of dying is imminent right there? So let's talk about it. So we have this question here, why do organisms age? So it kind of almost seems like something that you've maybe never thought of, unless you're weird and like me and asked that question on your 6th birthday and didn't really understand why you had to keep having birthdays. But why do we age? Why do we keep having birthdays? What is the purpose? What is the mystery? Well, there really is no mystery actually to it. We've actually kind of solved that problem with biology, and let me tell you how. So we have this phrase here, italicized: the force of natural selection lessens with advancing age. Now, what the heck does that even mean? Let me put it to you in this odd perspective here, guys. So you have a mutation that causes a person carrying it to die at the age of 10. This is a human person, mind you, not a cat person or something like that. We have a human person who has a mutation and they die at the age of 10. Now, what this means is this mutation makes it very unlikely that it will be passed on. Alternative versions of the gene, which don't cause death, will persist instead. So what happens is we essentially weed out, natural selection will weed out that mutation because that mutation is not passed on from that person carrying it because they died at the age of 10 to their offspring because they did not reach the age of reproduction. They were not able to have offspring, right? Now, in a different scenario, a mutation causes a person, a human person, carrying it to die at the age of 150. This mutation would be very likely to be passed on because they have well reached past that age of maturity to have offspring, to have reproduced and passed on that mutation that causes that person, their offspring, offspring, to die at the age of 150. Now imagine that mutation were to kill its carrier at the age of 100, or let's say 78, the average lifespan of a human. Are you picking up what I'm putting down? So, what we're saying through biology, guys, is that aging is evolutionarily designed, if you will, to be carried from generation to generation, to be passed on. And that is why we age. So I want to reiterate, because that was kind of heavy. If you think about it a little bit too long, it feels really heavy on your mind, if you're anything like me. So once again, if we're looking at that illustration there on the left, genetic disease and aging, it's saying that alleles that cause sickness and death early in life, potentially at the age of 10, that person will be killed, that will die. They do not reach sexual maturity. But if we have that death that occurs later in life, and that condition is passed on to their offspring, where they live to 150, and that condition is passed on, then that is essentially why we age. So natural selection will weed out diseases that cause death before puberty, thus aging, if we see it as essentially a disease or a mutation that kills us well after puberty, is able to be passed on generation after generation, which is kind of a wild way of thinking about it. But this is our best theory or hypothesis, however you want to think of it, because I don't know that it's coined as either from the book, of why we age. It is just a mutation, essentially. Kind of crazy, guys. Cool stuff. So what determines the lifespan of various species, which we will look at as longevity, which is what we called it in life histories. So longevity is going to be determined by essentially environmental risks or hazards, if you will. So high hazard factors are going to result in species that age very quickly. They have a relatively high risk of death at each age, and individuals tend to reproduce early, and they have earlier aging, so they appear to, like I said, age quickly, and they have more offspring. Their offspring will also have a high risk of dying, so they will have shorter lifespans. When we look at this kind of species, we're going to think like prey animals, like rodents. They usually have a pretty short lifespan. They're just not long for the world. They'll also typically be animals that are on the smaller side as well. On the other end of the spectrum, we have low hazard factors, and we have the example of a tortoise. These guys are going to age very slowly. They're very low risk of dying. They usually get larger in some capacity, can be larger animals. Their reproduction will come much later in life because there's no rush. If you live longer, and you have a low risk of being killed or eaten or whatever, then why rush to have offspring? But the kind of catch to that is that they tend to have less offspring as well. This slide essentially just repeats almost exactly what I just said, and I apologize for kind of repeating myself. But it does say that low hazard factors favor later reproduction. Later reproduction leads to longer lifespans, weeding out alleles that affect earlier aging. High hazard factors favor early reproduction. Early reproduction leads to shorter lifespan. And the only thing that I don't think are really talked about is that last little green box, and that is immediate environmental effects support these relationships, living in captivity versus living in the wild. So we look at a lot of studies actually of starting animals in captivity versus starting them in the wild, or animals that start in the wild. And animals that start in captivity are typically, fed on a regular basis. They have less stress. They are not subject to dying due to various reasons. Where we see animals have essentially induced low hazard factor favors, which is kind of interesting. But yeah, lots of cool studies on that. So, can we slow down the process of aging? Yeah, we sure can. Um, in the fact that we have just talked about, aging is essentially just a mutation of being able to live to 150 or something like that. Can we evolve, if you will, as a species, as a population, to live longer? Yeah. In fact, we have seen that done in flies. So in this group of fruit flies, what they've done is they took fruit flies and only bred the ones that lived longer. I think the initial fruit flies lived just a couple of hours, something like that. And then they increase the amount of days over the generations by only breeding the flies that live the longest. So it's sort of a survival of the survived, I guess, if you want to think of it that way. So by the 10-week generation time, however many generations that ended up being, but 10 weeks later, which, flies reproduce pretty quickly, so that was probably quite a few. 90 generations is what it says. My apologies. I'm not reading as fast as I'm seeing. So over 90 generations, over 10 weeks, they were able to almost double the longevity of the experiment, which is super cool. But that's one way to show that life extension is in fact possible. But for humans, we would not be able to live long enough to see that in effect, obviously. We reproduce very slowly. We live much longer lives. It would be very difficult to see our lifespan get longer. But we have seen the average lifespan of humans increase over our recorded history. So the average lifespan of a human has increased over the many years that we've been able to record what is essentially the average lifespan. So neat stuff. It is happening. We are staying alive a lot longer, but for various reasons, probably more due to technology than evolution at this point in time. So speaking of humans, we're really quite an interesting species, And in 2011, we hit somewhere around 7 billion people on Earth. As of 2024, we are sitting at a very uncomfortable 8.1 billion, which is a little bit terrifying. Plenty of fish in the sea kind of thing. There's so many people on the planet, and you start to wonder how high can our carrying capacity be lifted? Because remember, it's that little ceiling that every population will hit, and the earth can only hold so much of any species. And most species are confined to their environment, but humans are not. We are confined to the entire earth, but the earth can only hold so many of us. That number of how many humans the earth can hold has been greatly debated over many years, as well as what carrying capacity the earth actually is. That's been debated for about 300 years, and it changes constantly. But with that in mind, I don't want to leave you on a low note there. There are plenty of people who are working tirelessly to build a very strong tomorrow when it comes to our population and our environment. So potentially you could too. So let that be a little beacon of hope there. So we increased carrying capacity for the human population in kind of three ways, and we start to wonder, do we have limitless carrying capacity? And maybe not. Like I said on that last slide, it could be a good or a bad thing. We may be looking for a new planet sometime soon. Who knows? But we are very good at expanding into new habitats. We're very adaptable creatures, and we can pretty much survive anywhere on Earth. In fact, you can find humans on just about every continent. I think we're on every continent. Can't name one we're not on. And then we increase our agricultural productivity of our land. So farming is one of our greatest tools as far as species go. I think there's a handful of other species that use something mildly similar to farming, depending on how you look at the classification, but nowhere near what humans do. Obviously, we are very unique in that capacity. And then we find ways to live at really high densities. And when you think of that, I want you to think of a city, whether that be like St. Louis, or a really good example is Chicago or New York. Instead of building out, we build up. So think about buildings, how we have engineered the ability to make domiciles into really wild ways to have our habitats essentially, and live at higher densities of populations. It's really quite unique. So in the end, how many resources does each person on Earth need in looking at estimating carrying capacity, right? And in answer, it is so impossible to guess how many resources each person on Earth needs. What we can look at, though, is our ecological footprint, and that is the amount of resources essentially that a country uses is a little bit easier. And we can also look at it on an individual perspective, but that is even kind of hard to do. So less of looking at what does each person need, but what does each person produce as waste, is how we have looked at things from an ecology perspective. So we can look at land, food, water, and fuel, and then look at countries that have excess resources, and we can also look at countries worldwide that exceed resource availability. And if you'll notice, the US is the first one on that list. Unfortunately, we have a very unsustainable level of consumption. If you didn't guess, that would be us. And on that cheery note, and with this most excellent picture of three of my wonderful babes, that is the end of chapter 16. I hope you enjoyed it as much as I enjoyed lecturing you on this chapter. If you have any questions, comments, or concerns, you know how to find me, where to find me, how to contact me, and as always, make good choices.